Now, let me just change it up here. If, for example, I'm going to move our methyl group from carbon number 3 to carbon number 2. So now notice if this methyl's down, this one must be down as well. And so carbon number 2, in order for it to be down, it would have to be here or there. Equatorial or axial? Actually be axial, because it's really like kind of patronizing simple, just the fact that this hydrogen is above the methyl, so it's in the up position. So this one here now, the methyl's in the axial position when it's down. Here, if we're calling that one down, we're going to call this guy up because they're opposite of each other. So now our up position would be equatorial. And so now the trans is more stable because we have 2 in equatorial, whereas here we have 1 equatorial, 1 in axial.
Okay, so cis isn't always more stable.
Yeah.
Depends.
In fact, if a simple rule is if you have 2 substituents, cis is more stable if it's odd numbers. So if you have cis 1 3 or cis 1 5, you wouldn't have cis 1 5 because then you just number it backwards. You call it 1 3. Whereas trans is more stable if it's an odd number and even. So trans 1 2 or trans 1 4 will be our more stable. I think this is like sometimes the hardest thing to grasp is the up and down. Just
so how did you do that top one again? Like how did you know that the methyl?
Yeah, so if they're cis, they either both have to be down or up. The first, let me just walk through it, drawing it. And so the way I do it is I always say, okay, I'm going to pick my biggest substituent to be on this carbon. They're both methyl, so it doesn't even matter. And then I always want to put it in the equatorial, because molecules like to be as stable as possible. So I know one of them at least has to be equatorial, or the biggest one will be. And then I say, okay, this is cis to each other, and since being in the equatorial, it's down. If they're cis, the other one must be down as well. This one is on carbon number 2. So being down has to be in the axial position.
Because you can't, okay, so the other one couldn't be down, right?
Down here, this one?
No, that would have to be up. On the second card.
Here?
Yeah, that would have to be up, right?
Yep, that would be up.
Okay.
And so in the trans, if I'm calling this one down, if their trans are opposite, so the other methyl has to be up. So it would be there. And that makes them equatorial.
Okay.
And so a lot of examples, they have you remember your common name, the tert-butyl? Let's just draw it here. They'll have a tert-butyl group like this. And so a lot of the problems you'll do in the back of the chapter might be like, oh, cis, 1 tert-butyl, 3 methyl cyclohexane. And so what we'll do, our thought process, is we draw our chair conformation. And our tert-butyl is the biggest group. So we're going to put him, I'll just draw it like this, put him in the equatorial position here. And then we're going to say, okay, the methyl is on the 3rd carbon. So we'll go 1, 2, 3. And they're cis to each other, so they're both going to be down. So we know to draw him there. They're both. Now, if they were trans to each other, then our methyl group would have to be up here. Now before, what we could have done when we had our methyl groups, like when we were here, and one was equatorial, one was axial, we could flip them because cyclohexanes can flip. So then we could have said, oh well, one might flip and then we would have been this way. So then they're the exact same thing, and they're both just as stable because one's equatorial, one's axial, one's equatorial, one's axial. Here, this one won't flip because tert butyl is so big and so bulky, it has to be in our equatorial position. Does that make sense? Is that helpful? I think this, a lot of it's not like tricky, it's just understanding what they're saying and how they're drawing it.